to the KTH campus. This is what it looks like, not today, but in the summer. And mechanics department, wrong bottom. It's actually located in this building here. But I'm sitting in another building about 100 meters away where we have the laboratory. And I'll show you some of the things that we're doing in the laboratory. But let me just give you a short introduction to the mechanics department. There are 5 professors in the department. Myself, Dan Henningsson, you might know, Arne Johansson, who was actually the scientific secretary of the Research Council, at least the Science and Technology part, for 6 years, but now he's back in the department, and Gustav Hamberg is actually the Dean of the Science School at KTH. 2006, there was this program from the Research Council where they approved 20 centers of excellence all over Sweden in all different fields: humanities, medicine, technology, and science. And we were actually called the Linné centers, and we were actually got one of these centers, which is now called the Linné Flow Center. There's also some people from American Analysis and also from Acoustics in the center, but the main emphasis is at mechanics. And Dan was the first director, and now Arne is the director of the center. And this is not so much money actually into the flow. We get 5 million per year from the Research Council, but it's a very good opportunity for us. It's like, you know, this guy who had all these medals on the wall. He had this big medal, and then he had 8 smaller medals below. And then he said, the big medal I got by mistake, but the small ones I got because I got the big medal. Now, I hope we didn't get this medal by mistake, but it was very good for us to attract other funding. So we're involved in many different projects, both in Sweden, international, EU projects, etc. I can use it. And this is now just sort of focusing down on the fluid physics laboratory where I'm heading, but I have some very good colleagues. Jens Fransson, for instance, one of my former graduate students, he got one of these ERC grants for young investigators last year. So he has a lot of money to spend right now. Fredrik Lundell. Nils Tillmark is the one that I work with closely on, that I will talk about today, and then we have some guests that are regular guests: Rebecca Lindholm from Cambridge University, Palamelle from Bologna. So the talk that I'm going to give today is based on, well, it's been work that has been going on for quite some time. It already started in '96 with Nils Tillmark and myself, and then we laid it aside for a while, but then it gained some momentum again. And especially here, we had collaboration with Japanese colleagues. Shibatashi was a student who came for a couple of months, Professor Nagata at Kyoto University. But recently we had a postdoc, Takahiro Tsukahara from Tokyo University of Science, who came for 1 year, and then we worked a little bit after that. So a lot of the work that I present today is actually from this paper that was published about a year ago. Now, system rotation. I'm sort of coming from a different field, and so for us, system rotation is mainly because of engineering application. We have rotating machinery like turbines or compressors or wind turbines, or you can think about it. So there are many different aspects, and what I'm going to talk to you about today is the quiet flow. So 2 parallel walls moving in opposite directions. But you can also think about channel flows where you have a pressure gradient driving the flow. So, and there are some similarities, but some differences between these two. Another type of rotational flow that we have worked on, but I will not talk about today, is flows that are rotating along the sort of the flow direction. So the pipe flow rotating along the axial direction, and it's a quite interesting flow field because you break the symmetry with the rotation. So it shows some quite interesting aspects. But I can come for another talk talking about that. Something we did quite a while ago was also combining rotation with centrifugal forces. So this is a curved pressure-driven channel that we put it on a rotating table. And in this kind of flow, we introduce both centrifugal effects and Coriolis effect at the same time. And then depending on the rotation direction, we can either enhance the centrifugal effects or sort of go in the other direction. But I will not talk of that either today. And then maybe this is the most common example of centrifugalism, the Taylor-Quett flow, which shows a very large variety of different instabilities depending on how you rotate the two cylinders, counter-rotating or co-rotating. I can say that in a limit of a very small gap and both rotating in the same direction but with a small difference in rotation rate, you come to the planar Quett flow. But as we will see later on, there are a lot of similarities between this flow and the rotating Quett flow. And here are some other regimes for the Taylor-Quett flow, and many different type of instabilities. For instance, this one was discovered by Coles a long time ago in the 60s. He found regions of laminar flow which was intervened with turbulent flow. He called this a Barber pole turbulence. It's like one of these rotating Barber poles you can see in the snakes. Okay, so anyway, let me just show you another experiment that we're also doing right now in the lab. It's a rotating disk boundary layer. So here it's actually a disk that is rotating, and that's the only thing that sets up the flow itself. So it works more or less like a centrifugal fan. So it draws the fluid towards the disk and then it spreads in a very thin boundary layer on the disk. And this is actually the only flow field, wall-bounded flow field, where there has been a possibility to predict the transitional Reynolds number, where you actually can predict from first principles where transition to turbulence occurs. And that was actually done by Rebecca Lingwood in a doctoral work in the middle of the 90s in Cambridge. And now we have moved the apparatus. This is actually the same apparatus, but we have modified it to KTH. We have borrowed it from Cambridge, and we also borrowed Rebecca Lingwood, at least part-time, to KTH. So this is something that we are now working on both experimentally, and we also start up some direct numerical simulations of this flow field together with Philip Slatter. Okay, so now I will try to concentrate on the rotating plane Quett flow. And as we said, we have two walls moving in different directions, and for the laminar case, it's a very simple case. We get the linear velocity profile, and in principle, the only change compared to the non-rotating case is this term here, which includes the Coriolis acceleration, or Coriolis force, and the centrifugal force can be easily taken up into the pressure. So the equation is rather simple, and this is incompressible, and the experiments I will show you are in water. So it's incompressible. Now, we have two parameters that sort of governs this flow. And of course, the Reynolds number, which I define here as the wall velocity times half channel width and viscosity, as usual. And then we can choose how we want to characterize the rotation. Either we can do it in this way, so we have the rotation rate here, channel height squared viscosity, or as many do, they use what they call a rotation number, and this is just to confuse you because this is the opposite of the Rossby number, or the inverse of the Rossby number. But this is in the engineering literature, this is a common way to characterize the rotation. For theoretical analysis of the problem, it's very convenient to use the Reynolds number and the rotation number as the two parameters. From an experimental point, it's better to use the Reynolds number and the omega as parameters, because as you see in this flow, if we change the Reynolds number by changing the velocity, we will change the rotation number, so they are not independent. But if we change the velocity here, it will not affect this parameter. So it's, in an experiment, it's easy to, what you want to vary is either the rotation rate or the velocity. So then you can do that independent of each other.
Omega, you call the Taylor number normally, or not?
Yeah, actually it's usually the square of this that is Taylor number. But
yeah, it was Ekman number. Yeah. But, and why do I mean the Rossby number is really the inverse one? So
yeah, the Rossby number is inverse. Yeah.
Why did you call it like this?
No, and this is what the engineering literature uses actually.
Really?
Yeah. And it's sort of confusing because it's the same abbreviation.
We call it the Coriolis number, by the way.
Yeah. Okay, so maybe I should change that. But that is the standard way. And of course, the Coriolis effects comes in like that, and this I try to explain to people in a simple way why it doesn't really matter whether we move both walls in opposite direction or if we have one wall stationary and the other wall moving, because you can see this as just you can see this just as a superposition of these two flow fields, and of this, of course, there is no instability coming for constant velocity. And here you can, of course, see that if we have, depending on the way that we rotate, we will have either a stable stratification of the Coriolis force or an unstable stratification. So, and this now is, if we rotate it like this would be an unstable stratification of the Coriolis force. And if you do the, well, just non-dimensionalize your equation, the Reynolds number comes in here on the viscous term, and then the rotation term comes in either like this or like that. So that's, for the theoretical analysis, it's easier to use the rotation number like that. But then, of course, there is a very simple relation between the two. Okay, now if you do the linear stability analysis of this problem, it turns out to be quite simple. Well, the assumption that you do, and that's also what you observe in experiment, is that you create span-wise structures that are infinitely long, but have a certain span-wise wave number, so set this in along the rotation axis. And then if you put this assumption into the equation of motion, you get a sixth-order equation like that, like this one, where you have the non-dimensional numbers, Reynolds number, rotation number here, or if you prefer the omega, you get them like that. So that's quite straightforward.
So here you have no variation along the x direction.
No variation along the x direction, right? And that is actually what you observe for the neutral curve. So this is a neutral disturbance, so no growth rate. Just but of course you could put in either time dependence or x dependence. Time dependence would be the best here, which would give you the growth rate. Okay, so for the linear stability problem, it's better to work with these variables, the Reynolds number and the rotation number. You get the boundary condition, and then for the rotating plane quiet flow, this is a velocity derivative of the mean velocity. That's only that's equal to 1 because of the linear profile. And then actually, it is possible to solve this equation, or you can solve this analytically, actually, to find the critical Reynolds number. One thing that you can observe is that this, if this is minus 1, this term here is less than 0 for only this range. And this, it turns out to be the unstable range. If you're outside this range, it will always be stable. And actually, you can see immediately also that it will be symmetric around the rotation number 1/2. So that's why it's convenient to work theoretically with the rotation number. And actually, this is the critical Reynolds number that you can actually determine directly from the equation analytically. It's the same stability equation that you have for a Rayleigh stability. That is, if you have two walls, one is heated from below, and the other is at a lower temperature. Also, for that case, you can solve this analytically. And you might, if you have seen that problem, you might remember the number 1708. But if you take 16 times this, you get the same number. And this is just because of non-dimensionalization of what height you're using, etc. And this means that if this is the critical Reynolds number, you find that the lowest unstable Reynolds number is 20, which is extremely low. So for very low Reynolds number, you can get these instabilities. And the span-wise wavelength number is 3.1. So of course it's close to pi, which means that the roll cells, or the structures that you will obtain, has the same spanwise wavelengths as the height of the channel. And this is the neutral stability curve. So here you have the rotation axis on this, the Reynolds number here, and in this, above this line, you have the unstable region and stable below and to the sides. So and you see that it is symmetric around this line here. So that's a nice well. That's why one would prefer to use the rotation number when one does the stability analysis. Now, if we instead do an experiment, then we are more interested in using this parameter for the rotation, and then you can, of course, transform this equation for the critical Reynolds number, and then it looks something like this. And yeah, so and of course you see here omega has to be positive to have a positive critical Reynolds number. And in that kind of diagram, the neutral curve looks like this. So now we have the Reynolds number again here, the rotation in this new parameter here, and the neutral stability curve is this black line here. And then if you just draw lines of this rotation number, they will become straight line in this type of diagram. And as you can see, for instance, below rotation number 1, we said everything is stable, and asymptotically these two lines, of course, approach each other. Now when we do experiment, I will be in this part of the diagram, below 30, because that's the highest that we can go in the apparatus. We go to Reynolds number like 700, but we will be in this part of the diagram. But also for negative rotations, actually, because negative rotations, they are not, if you do the negative rotation, you actually stabilize the flow. Compared to making it unstable. And that has some effects on turbulence, as we will see. Okay, who has worked on this? Well, there has been quite, not so many, but quite a number of people. And of course, Quet was maybe the first one, but he didn't really do it to study stability. He built his apparatus to determine the viscosity of fluids. So he had an outer cylinder that rotated and had an inner cylinder with a very small gap in between, and he measured the torque on the inner cylinder to obtain the viscosity of the fluid. And then we built in the early 90s this apparatus that I will show you soon. At the same time, my colleague Arne Johansson did a direct numerical simulation of this. And at that point, what was interesting to find out, this was without rotation, to find when does the turbulent flow, when do you get transition in this type of flow. And then there have been other people here in Paris working with the same problem, and then also some new recent direct numerical simulation, also from France, actually, even though they are Americans. So not so many people, but still a few that has worked with this type of flow. And then there are other people who worked on the turbulent plate bed flow. Also, we have done that together with colleagues in Norway, also in our own department, Japan, etc. So there are a few. Now, if you want to do this experimentally, how do you realize a plane wet flow? It's not so easy because it's complicated in some sense. So there have been several ideas in the literature and also experiment. This is, for instance, one idea where you have a very long table. I think it was more than 20 meters, should be very flat, and then you have something that moves, a carriage that moves the plate on top of it. And then you can create it. But of course, it takes some time to set it up, and you have a limited measuring time. And you have to make sure that this is done in such a way that you actually get the right flow rate in here. So you have to catch enough fluid into the channel to get the right flow. So it's not really practical. Here's another way to get something that is moving, the so-called water table. So you let the water flow down an inclined plane, and then you create a surface that is moving at a certain velocity, and then if you have a plate up here, you will create a velocity profile. But also here, you have to make sure that you get the right amount of flow into the channel, so you have to create some kind of pressure gradient in the beginning. So it's not not so practical
But
actually.
it's steady at least, right? You have a steady, easily steady conditions. Whereas with a moving plate, once
Yeah.
you've moved the plate over, you're
Yeah,
done
yeah.
with
So
it.
then you have a shorter measuring time here. Yeah.
Yeah.
Yeah. So this could be a possibility to do. But it will still take some time before the flow profile develops nicely here. You have a development length that is maybe problematic. And then you have a more mechanical complicated system where you actually have moving belts. Either one belt on a stationary and one stationary surface or two moving belts. But also in this case, if you do that, you have to create a sort of a pressure gradient here to drive enough flow. Even if you make this infinitely long, you will never get the fully developed wet flow, which people sort of want to say something.
So this propeller might introduce some swirl.
Yeah, I mean, this is just to illustrate. This is not the way you do it, of course, but it's just to give you, in the beginning, a mixed Poiseuille wet flow. Because you have to have enough flow rate in here to develop this profile. Otherwise, typically, if you were just running the band, you will get the profile looking like that. And then it will never develop to the fully developed because you cannot add mass anywhere. And that will take some time before you develop the profile. We have done that actually, but it is complicated. But this is, of course, the way to do it best. Because here, you don't have to worry about inlet conditions because actually it turns out that they affect maybe the flow only for a few channel height. Here, the profile only depends on the viscous diffusion across. So it's so you just wait long enough, and then you will have the profile. Typically, the experiment is a few seconds. Yeah.
If you put this system in cavity chamber, this one, what flow will be not so good. But what do you think? If you put cavity chamber between two bands, it is will be more or less the same as in new system.
So you mean we put
Chamber in this some box between.
here? You mean? But then you will get the circulating flow.
What will you put between the two bands? It will be better than one band.
I'm not sure.
Good answer.
I mean, you could use this part here. Here you would get the profile correct. And this is actually what we do. This is actually what we do. Not having two bands like that. This is just a principle. We have one band like that, and then we have. Okay, that's what you meant.
No.
Yeah, but that's exactly what we do. Because if you use one band like this, then we are sure that we have the same velocity on both sides. This would be a complication with two separate bands. So let me now show. Okay, yeah, this is. Let's skip that one. No, let's skip it. Just to say a little bit about people who did work on rotating plane wet flow. The stability theory that I showed was fairly late. It was in 1976 that people realized that you got the Rayleigh problem if you have the wet flow, and there was Messrs. and Johnson from Stanford who did that. Then there have been DNS of rotating wet flow by Andersson in Trondheim, also by Johansson here at KTH, and then we did some early experiments as well. I would like to point out this, because we talked about it at the lunch also, Nagata from Kyoto University. He has found stable, what he called tertiary solutions for the plane wet flow, so non-linear solutions which are non-trivial for this, from DNS. And he found, if you remember the stability diagram again, the Reynolds number here, the rotation omega here, he found in these three regions what he called stable tertiary solutions, so complex non-linear solutions looking something like this. So one of the aims of this experimental study was to see whether we could reproduce one or several of these regions. So I'll come back to that, see if we succeeded. Okay, so this is the experimental setup. So, okay, now you see. Now I understood what you meant. So we have one band that moves around two big rollers. One is driving the flow, the one is just passive, moves along. Then we have so-called what we call steering cylinders here, so to have the band in the right position. The really smart thing with this experiment is that the band is made of a transparent material. It's like an overhead film. So you can look into it. It slides, it passes you, but you don't see it, as we will see in some videos later on. It slides along a glass plate here. So what we have here is really an aquarium. All these mechanisms can be lifted out. It slides along a glass plate. It has a very thin lubricating layer of water in between the glass plate and the band. It should be approximately 0.1 millimeter. Then it goes around here and slides along another glass plate on the backside. And when we built this first, we thought we should be able to use this also as in air. And then we ran it in air for the first time. And you know what happened? Well, it worked like a Van de Graaff generator. There's a lot of sparks moving around in the room. So we decided not to. It would have been a problem also to actually run it because it was flapping a lot. But the thing that saved us here was that we have the glass plate, so we are looking from this side, outside. We have the glass plate here, we have the band, and then the water level here should not cover the tip of the band, but we should have a water sitting here. And then surface tension makes the bands very close to and stabilizes the band. And when you do like that, it runs extremely smoothly around the surface. And then you have to make sure that these are at a certain distance, because if it's too small, suddenly it will just stop because the friction becomes too large.
What happens at the end of when the double cylinders are, what's the return flow
Yeah.
like?
Of course, here it becomes quite complex, and if we are above a certain Reynolds number, we will sort of mix here and we will start turbulence at the ends, and then the turbulence will grow inside from the ends. If we are below a certain Reynolds number, they mixes, but then disturbances dies away. And typically, then you will have maybe entrance effects for maybe 1 or 2, 3 channel heights. And this is, 150 channel heights, so the central part is not really affected. But if the Reynolds number is high enough, then turbulence starts at the two ends and grows into the channel.
How do you control the presence of some torsion when you have rotation? It must be some oscillation which is used to that.
Yeah, but it's small. Rotation is very low. We have some waves on the. Yeah, you have to balance it very, very good. But still, you can see it. We have seen it when we did. We cannot really see it in the flow visualization, but we can see it when we measure.
If the engine, what you call motor, is stopped and it's only rotating, so what happens to the flow?
Yeah, that's. Unfortunately, I don't have it here today, but we did that experiment, and actually, then you develop another type of disturbance. Well, it depends on what the Reynolds number is. But if you have the okay, that's another page. Okay, so what you're saying is you have the two bands, one is moving that, and one is so we have the linear profile like that. Okay, now we stop the bands. Okay, what you develop then is a velocity profile like that, which turns out to be unstable, and you create disturbance in this direction, in the spanwise direction. So roll cells that are sitting like that. It's an inflection and instability. We did a paper on that. We call it the Rayleigh instability.
What is the thickness of weighted channel?
Actually, that can be varied because this glass plate here on the backside can be moved. So it's just a false wall. But what you see today is in the photographs is 10 millimeter, in the videos is 20 millimeter. So 10 millimeter the full width for all the photographs and 20 millimeters for the videos. So for 10 millimeters it's pretty good aspect ratio. 20. Yeah. You see the same things, but okay. So this is what it actually looks like in real life with the right proportions. And Axel has seen it, so it exists also. Just we have the camera on the rotating table to light sources like that. It's driven from outside. We have the possibility to get power into the system. We have rotating electrical couplings both above and below. This is what it looks like in well, part of it. This is the test section. Just to one important thing is, of course, to determine the width of the channel. And we have a microscope where we should focus on one wall and then on the other, and then see the distance in between using the refractive index of water. So we can determine it within 1 or 2%, we think. And this is just on the back side. This is the driving cylinder. You see the two steering cylinders here. Now it's not filled up completely. The band is somewhere in there. Okay. Now, what I will show you today is mainly flow visualization of the flow. And this is a typical picture at a low Reynolds number with unstable rotation. So the bands are moving in vertical directions. This is about 4 centimeters. And you can see these white and dark bands here. And what we do here in this flow field, we add these reflective particles or platelets. The same type of platelets that you have in shampoo or soap, you know. Or if you want to put some glitter on your eyes, it's the same type of particles. It's very cheap, actually, if you buy them for this kind of experiment. If you buy them as cosmetic, it's extremely expensive. So you should go to the right store when you buy this. And what happens in this flow field, we have these kind of counter-rotating rosas, and they orient these particles in various ways, and then they will appear either dark regions, and this is just a blow up on part of this region. So you have the white regions, black regions. So depending on where these rosas are, you will, or how they are oriented, you will see bright or black parts. It doesn't come out very well there, but that's the whole idea. If you have other types of structures, you will see them also. Okay, first of all, we try to determine the critical Reynolds number, and this is one of our Japanese colleagues who did this in our experiment. So this was his measurement points where he thought he started to see the row cells. The red curve is a neutral stability curve, so it seemed to confirm the theory quite well. So we were happy.
What is black?
And black was just actually least, no, it was the least square foot to the black points. Okay, now this is now a very complicated diagram. These are the two parameters where we run the experiment. Reynolds number here, rotation rate here. From positive omega, we have unstable rotation or anticyclonic. For negative, we have stable rotation or cyclonic rotation. And as you see, there are many different regimes here. We try to characterize the different flows that we see. And I think we ended up with 17 different regimes. Everything from the laminar flow here to very complex three-dimensional flow with turbulence in that regime. And I will show you a few things that I will not go through all of them, but a few of them. Okay, let's start with zero rotation. Then we just have the two walls moving. So what will happen if you do that is that it will be laminar up to a certain point where we will form turbulent spots. It's actually this regime here. And then if we move on, we get what we call turbulent stripes, intermittent turbulence, and then what we call featureless turbulence. Now I will show you.
What does it mean featureless? No something?
No structures that we can see. Yeah.
Just turbulence.
Just turbulence, ordinary turbulence. And that extends in this direction and also in that direction.
Turbulent spot, into spot. It is more or less ordinary turbulence or something?
No, it's a region. It's a spot of turbulence, I would say.
But into spot, how is it?
I will show you while you see a photograph of it. Okay, so this was just to show you. This was Tsukahara. He spent a lot of time in the lab doing more than 400 characterizations of different flow states, moving, changing omega, keeping Reynolds number constant, or having an omega moving Reynolds number, both up and down to see whether there was any hysteresis in these. But he didn't find any hysteresis, actually, at least if he waited long enough. And all these different symbols mean different things then. So I will not go. So this is what it looks when it's laminar flow. So here you have about 35 centimeters height, so this would probably be about a meter in this direction. And when it's laminar, you don't see anything. It's complete. This is just, don't worry about this. This is something on the glass plate on the other side. It does not disturb the flow.
Just ask back again about the previous plot. You have stabilization by rotation.
Let's go back to this one more.
But you plotted this as in a linear scale, both axes. Are these power laws? Would they correspond to power laws? And what would be the slope then?
Don't know. And this looks more like a linear increase if you subtract, if you would have subtracted the sort of the transition.
You would maybe expect a omega to this maybe 2/3 type of scaling band.
That could be checked.
What do you have for
just oscillations, neutral oscillation on the left hand side, and the normal turbulence, nothing else.
The longmost line certainly is just the onset of turbulence or instability, and that's being stabilized by rotation. I expect it to be some power.
Could be. I haven't realized. Maybe the range is too small.
Yeah.
Here is the neutral stability curve, by the way. This one now.
Yeah.
That you saw before.
Then shear doesn't enter in these parameters, yeah?
What?
Shear. Value of shear doesn't enter.
No, it doesn't enter, no.
Okay.
And it's constant here also.
It's constant here.
But the Reynolds number is unproduced shear.
Yeah, you could say that.
Yes.
Okay, let me just show you now. We are now on this side. Here is the diagram. So we are now here around this level. We start, this is from up here. This is what we call intermittent turbulence. So you can see very random flow field of small scales mainly, but there are some regions of laminar flow. Then if you go to what we call the turbulent stride, then you have regions of laminar flow that is stretching across the channel. This we think is similar to the barber pole turbulence that Coles observed. And here is what we call a turbulent spot. You see that? Then we have a turbulent region which is surrounded by laminar flow.
You destroy stripe as a result, right? Sometimes you destroy. You structure with stripe, and what?
Yeah, I mean, if you go this direction, this laminar region will sort of...
But it's stripe, it's something elongated.
yes, elongate at a certain angle, yeah.
And after that, it's just destroyed even with this stripe.
Yeah, and then you get sort of part of it becomes a turbulent spot, which may grow or decay and move around. And you see there's some structures here also elongated in front of them. And typically if you create a turbulent spot at a sufficiently high Reynolds number, it starts to grow, but it will be preceded by these streaks in front and in the back and also on the sides.
And what typical time of life of this sport?
Many minutes or many
Many minutes.
Many
Very
minutes, yeah.
stable.
Yeah.
And stripe of course too.
Yeah, stripes also stable, yeah.
You didn't see any hysteresis.
I couldn't see, no, that was the conclusion. Okay, so now I would like to show you, let's see, could we get down the, maybe it will be an office. Okay, so here we are at the Reynolds number 700, so it's turbulence. And no rotation to start with, that's why I say final. And then we start to rotate it now in the negative direction, so we're stabilizing direction. And then what you will see in the end is that the turbulence has actually died down. Let's see if I can get this to start. Okay, so here is the turbulence. The nice thing with it is that there is here you can see a scratch in the band. So you see the speed of the band. But otherwise you don't really see it. And
So that gives you marker. It's a good
yeah.
marker.
And now we have started to rotate, as you see. And you can see that the turbulence just dies away. And here is the joint. Now it looks as if not stable, but this is my movie, or my computer that is not fast enough. It's really very. And in the end, it becomes completely level. So I will show it once more.
So, Reynolds 700.
Yeah. So we are. I mean, if we're not rotating. This is fully turbulent, I would say. And then at some point here we start to rotate it. I can see it up there. Now it's rotating.
There's no measurement of the fluctuating velocity, right?
Now,
This is the law of, it's very interesting law.
and you see it's completely dancing. So it's a way to control turbulence, but I don't think it's a very practical way.
So Reynolds number based on the turbulence parameter is about 70 to 10 times less.
Oh, okay.
If
I cannot tell you.
Hmm?
I cannot tell you, but if you say so, I believe you. Okay, so why is this happening? I mean, you can actually, I think you can understand it directly from the equation for the Reynolds stresses, or for the turbulent kinetic energy. This is just the Reynolds stress equation in general form. You have sort of this term which shows how they develop, and then you have the production term, pressure strain term, viscous dissipation term, diffusion terms, and that's the system rotation term. But here I think for this effect, it's not really dissipation that comes in, and these are probably not so important. It's the ordinary production term and the system rotation term that are the important ones. And if we write this equation down into the sort of the four important components, the string-wise variance or energy, normal, span-wise, and the sort of Reynolds stress producing term. The other cross terms are zero in this flow also because of symmetry. So here we have, well, it will look like that. If I go to the next slide and just have the...
The stress energy tensor is not symmetric for this, no? Should not be symmetric.
UV,
Not with rotation, at least.
It is similar to boundary layer.
yeah, it's similar. So VW and UW are both zero because of symmetry, also here. It's only this one actually that is non-zero. In this case.
D1, D1, D2, D should be negative. And
Yes. Let me go to this one, because here we see what I think are the important terms. These are this is the ordinary production term, and then the rotation term comes in here. There is no production term for the W, but for V you have it, and here you can see that this term is exactly the same as this one, but with opposite sign. So you transfer energy from one to the other. And then you have it for UV also. So, for instance, if it's say destabilizing rotation, then so anticyclonic, then the rotation number is positive. So this would be positive. U prime is 1. Let's see now. So we will, and this is positive because UV is negative in itself. So if you have positive rotation, we will produce less of U square. But we will produce more of V square. Nothing happens here. We produce more of V square, less of U square, more of V square. Rotation was positive. But in the end, we probably produce more of this, which then sort of enhances itself. If you do the opposite with a negative rotation, you will see that you will produce more of this or less of that, which will sort of stabilize the flow. So the V component is very essential for the production of turbulence. It's one moment. So I think it's possible to understand what we see from the energy.
This is the argument which Steve Barlows has used in his papers to argue that if you had hydrodynamic turbulence, the UV stress would always have the wrong sign coefficient disks. Exactly the same argument. And I think the reason why that argument was actually still wrong is because the pressure terms are neglected here.
Mm-hmm. Yeah, yeah.
And so
It's not obvious at least.
what?
It is not obvious what will be in reality.
Here, pressure term is introduced in the divergence of third moments.
It's simple and
Well, you have the pressure terms here, of course,
Yeah.
which is a redistribution term. So, of course, this is a very simplified model, and all of these components have, of course, a y dependence as well. Or sort of dependence.
Maybe it's not so bad. This is real sim system.
So which type of fluid is this one?
This is just water.
If you change the temperature a bit,
I mean, we only change the Reynolds number. So it comes in there.
I think another problem of Barlow that he hadn't this scene square, this 3D system. Maybe it's, all arguments is wrong simple for Barlow.
Okay. Anyway, let me now go to the V-stable, because it's actually even more interesting, at least from an aesthetic point of view, I would say. So here you see that region, and again a lot of these different measurement points, and here we have many more types of instabilities, and I will only show you a few, and it becomes very complicated, you can see. What we also did here, and Sukahara was very smart, you see these fluidizations, we have some uneven light distribution there, but he was able to enhance it with some smart techniques, so we could actually get much better contrast in the pictures. And from these kind of pictures we were able to then use just the correlation between the brightness to obtain the wavelength. So in that sense we didn't have to count or measure it. We could actually make correlation functions. This is a correlation function in the spanwise direction, so we could actually obtain the wavelengths in some kind of non-arbitrary manner, and also in the streamwise direction. But here they are very straight, so there is no streamwise wavelength. But later on we will see that we can get streamwise waves as well. So this is, you see, very close to the stability limit. So Reynolds number 52.6. So we are down here somewhere.
And correlation length here is about 1 delta Z divided by H.
Yeah, this is, I mean, for H here, this is between two
This one.
rule cells with one in between.
Oh,
So then it's 2H, one rule cell, so it's exactly what you would expect from theory. Okay, so now I'll show you another movie. Now we have unstable rotation. Reynolds number 200, so we would not get turbulence here. We start running just the band, so we'll have the fully developed bed flow, and then we start to rotate. So let's see if we can start it. And now you see, now we have a low Reynolds number, so the band is moving slower than before. And we started to rotate, and you see they immediately appear, the row cells, not so symmetric at first, because we are not disturbing it in any way, so they try to find their own wavelengths. But at this Reynolds number, it's actually not stable, this situation. Here's some disturbance coming, but if you look on this side, you will see that there is these waves become three-dimensional after a while. So you see now how they become wavy and they start to sort of go into each other. It becomes quite beautiful after a while, and complex. So this is one, what we call the three-dimensional laminar rose cells. And the videos were made a long time ago, in 95. When Sukahara came here, we know again about the Nagata solution. So then we tried to actually locate them. And this is a picture where he actually found at approximately the same Reynolds number in omega where Nagata predicted these stable 3D laminar rose cells, so nonlinear rose cells. And this picture sort of remained there for long times. So it was really stable.
So you have an aspect ratio here between the horizontal and the vertical
Mhm.
length, which looks like maybe around 4.
Yeah.
Is that...
We did a comparison with what he obtained for, and it was not exactly the same, but it was like within 10%. It is in that paper that we wrote.
And that's independent of omega or the other parameters? More
No,
or less,
I mean,
or-
here it's for a very specific
Yeah.
Reynolds number and omega. This was
This is aspect ratio.
yeah, that will change, both, but it turns out that the span-wise wavelength is always very close to 2H.
Ah, yes.
But the stream-wise wavelength may change. So again, it was just say that we are exactly in here, 8.7, 100. So this is
Nagata solution is a result of linear analysis.
no, it's actually the way he did it. He was actually doing Taylor-Quet. He started in the Taylor-Quet flow, and then I'm not sure how he did it, but it's a DNS. So
It's a numerical solution.
it's a numerical solution.
Ah,
Yeah,
it's
it's
a
a numerical solution. Yeah.
Not linear.
It's numerical solution. Yeah. I'm not sure any longer on the details because it did different things. Okay.
Because it's numerical.
Yeah,
not
yeah,
the-
yeah. Oh. So you can see, of course, for us it would be very interesting to measure the flow field here, but it's very hard to do that.
So you don't believe for anything else to do with solution?
I believe.
Good, good.
Okay, so this is another case, a higher Reynolds number now, larger omega, so we are back here somewhere. And this is what we call contained turbulence. There is some kind of three-dimensional rose cells which have turbulence inside them. This was a smart way to do it. Here it took with a short exposure time, so you actually can catch the turbulent fluctuation. Here I have the exposure time of 2 seconds. You see all the turbulence is actually averaged out, but you can see behind it, it's really something that is very stable. So there is turbulence inside this structure. And here is another case, similar but slightly different type of turbulence. We call these ripples. We can argue about them.
Can you try to perform ensemble averaging using different maps with different exposure time, and then
Subtract.
then it's possible to perform averaging,
Yeah.
ensemble averaging.
Actually, we did that but not in turbulence actually, but because I'm not sure what you actually will measure for the ensemble average. Let me show you, I think I have two more videos. This is different from the previous one. Here we start with a rotation and no flow, and then we start the bands. Okay? So first solid body rotation, and then the bands are started. So now we started the band, it was already rotating. And now you will see that quite soon we will see these streaks appearing here. And now they become unstable and break down to turbulence very clearly. And so now we have the turbulence, but after a while the rotation comes in, and you will get, even in the turbulent flow, get the roses, longitudinal roses. So you can see here now that we are forming these roses. You see the boundaries between them. It really looks like the turbulence is contained inside the roses there.
It seems that the turbulence in this case started from the boundary.
Yeah. Actually, this is exactly what happens here when we start the band. So from the beginning there is no velocity at all, and then we start the band, it will take some while before the fully developed profile is developed. So we will have, in the beginning, something that looks like this. Of course, here we have the band velocity. And it's actually these regions that become unstable. And that's also why we saw that the span-wise scale was much smaller in this, when we formed the first row cell.
So it's a boundary layer.
Yeah, in that case it's a boundary layer. And again, it seems like the row cells that wants to form has about an aspect ratio of 1. So here it develops within that region, and then the span-wise scale becomes a section of that size. So that's why they become small. I would like to show you this one again, because I think it's so beautiful. Especially the breakdown of the streaks is nice. So here they start to form, and you see very narrow here, and then you have this breakdown many places simultaneously. Fairly short wavelengths in the streamwise direction. And then you have the fully developed turbulence, and then after a while the roll cells forms in the turbulent regime instead. And it seems really like the turbulence is contained within the roll cells.
And this continues if you...
Yeah, this we can run forever. I mean,
Yeah,
that's
with the turbulence inside of it.
Yeah, it really looks like it's contained. But it might be just because the flow is hallucination, of course. But it really seems, you can follow sort of what is inside. And this is, let's see, here we are doing the opposite now. We have fully developed turbulence from the beginning, and then we start the rotation. So this is what it looks like without any rotation. So there are no structures here now, just the turbulence, and then we start to rotate it, and I think we have done it now. And you can see that we form the row cells. Okay, and also here you can, maybe even more apparent, it really seems like there's not really a correlation between the turbulence there and there. It really seems like it's contained.
Omega in direction, in this direction?
No, this direction.
Only
No,
in this
yeah,
direction,
yeah.
okay.
Yeah. That's
So you have here generation of inertial waves.
if you say so. That's
So the vertical, you approximately see the entire vertical extent of the band.
Yeah, here's the down. We have a measuring band.
And then in the horizontal direction, you see maybe.
It's less. It's longer than this.
Yeah.
It's approximately half the channel, I would guess.
Half already,
Yeah.
yeah.
So we have maybe ends there and
Yeah.
You can't tilt the band or operate it horizontally?
no, not with the open surface that we have. Okay, so this just to illustrate that, I have shown you a few different things. Maybe this is an interesting, what we call quasi-turbulence. We call it spatial temporal turbulence, because here you can observe how you form row cells. They become first two-dimensional, they become three-dimensional, they break down into turbulence. You have turbulence, the turbulence disappears, you have laminar flow, and then you have a cycle that repeats itself. So unfortunately I didn't have a video, but so that's an interesting. So I will conclude now. Just say that we think we have a very rich flow field here. We think that we have verified at least one of these cases that Nagata observed. That turbulence can be distinguished by rotation, we have also seen, and maybe there are a few other conclusions that you surely can draw. And I just want to acknowledge the people that have worked with us on this, especially Tsukahara, who did all this very tiresome mapping of the different flow states. Iwatashi and Nagata was involved with him. And then, of course, Ms. Gilmark, who is really the engineer behind the apparatus, and we did the first studies together also. Okay, so I think that was my last slide, actually. Yeah.
Any questions, please?
When you calculated two-point correlation function. So you have data of light intensity of these pictures?
Yeah, it should be somewhere. We should be able to have it. It is Iwatashi oh no, it's Tsukahara who has it all, of course. But you mean this kind of pictures?
Yeah.
Yeah.
Mhm.
So the pictures exist, yeah, sure.
Uh-huh.
And then and they exist in also a digital format, of course.
Mhm.
So you can obtain
Okay.
it.
Mhm. Mhm. So in some sense you have information about the velocity field. So all maybe density of these density fluctuations or number density fluctuations of this.
Yeah, but you know, they are not spherical particles. So what you see here is, I mean, if it's lighter, it's just because the particles orient them in a certain direction.
Mhm.
It's not that we have more particles there.
Mhm.
And the other thing is, you said that we have the velocity, yeah, maybe, but on the other hand, we don't know where the particles are.
Yeah.
So this is a sort of an integrated picture.
Okay, yes.
Yeah, nothing.
Could you try to use PIV system, because I think it will be very useful.
Yeah, actually, we did some tries with the PIV, and we have some slides, but we never really pursued it. It was not. Then you have to put everything on the rotating table, which
Yes.
is
I
another
know,
side.
of course.
It's complicated.
Why don't you
Yeah.
take them, because it's very expensive.
Yeah, it's complicated. The LDV we also use the test, but also now you have to put everything on the rotating. It's possible, but we really didn't.
You should increase your rotating table drastically.
You have these turbulent spots, and it was observed that they come with a certain angle.
The turbulent stripes, you mean?
The stripes come with an angle, but the spots also still had a certain elongation.
Yeah, but that depends on the Reynolds number, actually. If you go back to the turbulent spots here.
Yeah, and I was actually expecting it should depend on the Rossby number instead, because you would expect it to be proportional to. I mean, maybe the tangents of this angle should be equal to 2 omega times tau, which is your Coriolis, or what we call the Coriolis number, which is your rotation number.
But I can say that these also exist, actually, it turns out, without any rotation. So even if you're along
Yeah.
this axis, you can see these.
Sorry, yeah. Sorry, I was wrong. I meant S, of course. Then it's different.
Yeah.
And that is indeed related to the Reynolds.
So that is related to the Reynolds
Yeah,
number,
yeah, yeah, that's of course.
Right.
Thanks.
But this rotation number is based on the computed time of viscosity.
Yeah, right. You wanted, so therefore you wanted to divide out the Taylor number, of course, or this omega thing.
Yeah.
So then it becomes a more complicated construct. I mean, that's really the quantity you want. But that's neither the Reynolds number, but it's a combination of all three numbers. Because of the way they're defined. Any other questions? Yes?
Related to the structure, even in the turbulence case.
Yeah.
So what determines the dimension of
I mean, I cannot say but what we find is that the road cells seems to want to have an aspect ratio of 1. So they are and they are limited by the width of the channel, and then the span-wise width becomes the same as the channel width. So they seem to want, I mean, it's some way inherent that they become aspect ratio 1. More or less.
It depends on the S strain or some rotation shear, or how much shear will.
But we have done some measurements on this, and it seems to be fairly independent of that, I would say. It is more the channel width that is determines.
You change for the shear parameter also, yeah?
Yeah, we do that with the Reynolds number.
Uh-huh.
I mean, because the non-dimensional we have always shear 1.
Larger Reynolds number, you have more stripes, or the number of...
I cannot tell you actually. But there have been numerical simulation of this by this Tuckerman, for instance. And I'm not sure, and also actually in our department lately. So there are some simulations. I'm not really updating what they found. But they should be easier for them to say whether it changes or not.
You discussed the evolution equations for the stress test, u squared, but then you also had u times v. Is there any way of measuring or getting some measure of these quantities from the experiment?
No, not from the flow visualization levels. I would say that the flow visualization that we have done, that's perfect to sort of map out parameter space, to find the different regions. Now, to do what you suggest here, I would leave to the DNS people, because they could do this. But from our maps, they could find, what parameters to do the DNS.
And the agreement was a pretty good one.
Yeah, well, the ones that are done are pretty good.
Yes.
But of course, the DNS they are very time-consuming for this case. It turns out that the quest flow, you need a much longer box to get down to correlations to 0 than you do, for instance, in Poisson flow. So it's a much more demanding case for DNS than the pressure-driven flows.
Even longer than the experiment is.
No, this would be sufficient. But it's still, if you have 100 channelizers.
Right.
Without rotation, these measurements were done by Paul Gros in the middle 60s, but without rotation.
Yeah.
I mean, u square, v square, w square, all this stuff.
Yeah, but
That's
that
really mad.
but that was for the not for quest flow, Poisson flow.
No,
Yeah, it was. I read a thesis. But now, of course, we have that we have all these from the DNS simulations.
But again, better provision.
Okay. Yes?
How would you in principle measure the velocities
In this flow? I think PIV would be, we have both done LDV and PIV. So PIV, you know PIV? No, PIV is in principle you don't have these kind of particles. You have spherical small particles that reflect light. And then you put in a laser sheet, for instance, from the top here. Here. The distance where you want to measure. And then you put the camera in front of here. Take a double exposure. You determine the time between the exposure depending on the time scale. And what you can do is actually see how the particles has moved.
So it's an image analysis.
It's an image analysis. So PIV means particle image velocimetry. And then you will get the flow field in a plane, but usually only 2 components in that plane. You have to please also get the third component. If you want to do point-wise measurements, then you can use the LDV, which in principle is you have 2 laser beams that you meet in one point, and you can measure the velocity in that point in one direction actually. But then you also have to have particles in the flow field, because you actually measure the particle velocity, not the fluid velocity.
How would the particles actually affect the critical Reynolds numbers?
It depends. I mean, you should have very small particles, and you should not have a very dense suspension. You should have not too many, not too few either. In this case, I would. I mean, for the measurements, it would not affect. If you want to, if you wanted to affect it, if you put in enough particles, you could surely affect it. I'm not sure which direction. But usually, you increase the viscosity when you have particles into the fluids.
There's also things like streamer instability in protoplanetary display. You actually get collective phenomena in streamer particles.
Yeah, that's I know that you can get that also in cellular flows actually.
That's inertial particle.
Yeah, that's what for inertial particle. Yeah, here you want the particles, of course, to be neutrally buoyant. I mean, so it's close. So in water, it's usually not such a problem. If you do experiments in air, it could be a worse problem.
Yes, particles may be very expensive.
We could use the next 15 minutes to talk to Henrik informally over coffee, but let me remind you that we have a licentiate thesis at 3 o'clock. few months. And so with this, let's thank Henrik for a very interesting talk.
Thank you very much for inviting me. Very interesting. Okay.